Right. So you can also do these kind of hybrid things where you're talking about dy dx as a function of t if you want. Es bueno. Okay. So let's talk about arc length. So how do you calculate arc length? Do you guys know? I don't think you covered that in Calc 1, did you? I don't think so, right? So I'm pretty sure this is new. Yeah. Integrate the distance formula is that's kind of the right idea. So let me draw a picture. So if we have a curve, right, like this, and we want to calculate the distance, I think using the distance formula is a good idea. But the distance formula gives me the distance between for a line segment, right? But a way we could approximate it would be to say start from here and go to there, right? And then I could like go to there, then I could go to there, and then I could go to there, like that, right? And so if this was, you know, the initial point was, let's say, r of t 0, and over here I have, well, let me say r of, let me use a and b, r of a, and over here we've got r of b, right? So I'm talking about a curve which is parametrized, say by a and b goes to the curve which is a subset of R2. So we've got this curve, and what I'm saying is you could approximate it by you could use line segments to approximate the arc length, right? And yeah, why not? And so if we did that, we would have a formula for the arc length, something like this, right? So the arc length is approximately what? The sum. Let's see. So we're going, I guess we should take this and partition it, right? So partition it into like T0 to T1, T2 to T1 to T2, you know, our usual song and dance. Tn minus 1 to Tn, right? Where delta T is B minus A over N. So take the domain and partition the domain into n equal time segments, and then you'll have correspondingly n equal little displacements on the arc like that. And so in any particular one, your curve might look like, your curve might look like this, right? To start with, you've got, let's say, r of tj, let me say tj minus 1. And over here, you've got r of tj, right? So that I'm just zooming in on one of the little segments, right? And then if we use the, what's this straight line distance between these 2 points? Well, we can look at the distance, like the length of r of tj minus r of tj minus 1, right? What's the formula for that? Well, that's straight up the square root of x of tj minus x of tj minus 1 quantity squared plus parentheses y of tj minus y of tj minus 1 quantity squared. That would be the length of, that would be the distance formula for just, that's not going to give us the exact arc length for the curve, right? That's an approximation for the arc length of that little segment, but it's a reasonable approximation, isn't it? So we've got a sum, j equals 1 to n, of the square root of, you know, that stuff. And so, good. So for the interest of not going nuts, I'm going to call this delta x, and I'm going to call this delta y, because it gives me no joy to write those symbols again. Okay, so delta x squared plus delta y squared, yeah? So let me suggest this. We could take this and we could rewrite this as the sum, j equals 1 to n, of the square root of delta, my bad, my dx's are showing, delta x over delta t, quantity squared, plus delta y, delta t, quantity squared, and pull out a delta t. Sorry, poor planning on my part. Huh. Well, why would I do such a thing? Yeah.
Because, like, as your delta t approaches 0, you start to get that instantaneous rate of change.
Right, right. As my delta t goes to 0, these should become derivatives, right? To be more systematic, we can apply the mean value theorem on each subinterval to choose, right, to choose a specific time increment. Like this is equal to the sum, j equals 1 to n of the square root of x prime of tj star squared plus y prime of tj star squared times delta t. By the mean value theorem, there exists such a time in the time interval such that the average rate of change is equal to the instantaneous rate of change. This is the mean value theorem. I can apply it to x, I can apply it to y, assuming what? Assuming that x and y, the parameterization formulas, meet the criteria for the mean value theorem. What are those criteria? Continuous and differentiable, right? And then you're exactly right. So that's how they become derivatives. And then as we take the limit as n goes to infinity, what's this give us? This is the Riemann sum, right? This is the Riemann sum. So this motivates the formula for arc length, namely s is equal to the integral from a to b of the square root of dx dt, quantity squared, plus dy dt, quantity squared, dt. And that, my friends, is the formula for arc length. It's a consequence of the distance formula and the mean value theorem and the definition of the Riemann integral. Now that we have this formula, let's use it. Let's use it on example 3. Well, slightly twisted, but basically example 3. So where am I? Example 6, 7? I don't know. Feels like 6. You've got x equals to r cosine t. You've got y equals to r sine t. Let's calculate the arc length. Integral from 0 to 2 pi of the square root of what do we got? Dx dt squared plus dy dt squared dt. How those work out here? Dx dt is minus r sine t. Got to square that thing. Dy dt is r cosine t. We got to square that thing. Integrate that. You could do the algebra. How does that work out? Sine squared plus cosine squared is what? Right, because that, I'm assuming, of course, that r is positive, right? Should have said that. So what do we get? This is what? 2 pi r. This you should already know, right? But today, we derived it. Right? This is how we can show that the arc length of a circle is 2 pi r. So can you calculate the arc length of anything? Well, no. This is a dangerous formula. It's a very dangerous formula. Look at it. You're differentiating things, you're squaring them, you're adding them together, and then you're square rooting it. So yeah, I mean, there's hope for certain examples, but by and large, that most paths, you end up needing to use a numerical technique to actually calculate this integral, right? But the question? Oh, here. So one example to end with today. Oh, fine. I'll do it here. So suppose you take this path, right? Let's say 3 this way, 4 that way. How far is that? 7, right? 7. Now I'm talking about the distance, the actual length of the lines. 7. A 7. All right, 7. Great, great. So how about, what if I go halvesies? How far did I go? 7. Very good, very good. Quartersies. How far did I go? 7. All right, very good. Eighthsies. How far did I go? 7, right? 16ths. How far did I go? 7. Take the limit. Right? Clearly this staircase approaches this line, right? And no matter how many stair steps you take, as long as they're all horizontal and vertical, still length 7. But how long is that line? It's 5. So what's the problem? Yeah. Is it really differentiable? That's right. That's the problem, is that what I just did is not it's not like this, right? It's not well, the curve, well, I'm not really, for one thing, I'm not actually finding, it is not in if I actually look at the dotted line, right? The stair steps are in no way a piecewise linear approximation of the curve like in our derivation, right? But yes, also the real problem is that the stair steps are not smooth. It's not a smooth curve. It's infinitely jagged, right? And that's where it breaks down. But that's why smoothness matters and why you have to be careful taking things to the limit, because sometimes something in the limit could change in some sense. I mean, you see what I'm saying? But anyway, this is sometimes used as a proof that the Pythagorean theorem is wrong, of course, which I find amusing. I have deprived you of the rule for d squared y dx squared. I'll try to get that tomorrow. Yeah.
Did you get our test?
Oh, your test. Yeah, you have your test to go back. You can hit the Mr. Ham. You can stop the. Yeah, just the other on the other side. The big. Yeah. You got. Yep.